All right. Can everybody hear me? All right. Great. Great to see you all. If anybody needs assurance that AGI is not around the corner, I always feel that going to any artificial intelligence conference at any time and seeing how mightily we always struggle to set up the AV equipment is always a nice, you know, provides that assurance. So, you know, but who knows? Maybe building the artificial brain is easy, and setting up the projector is just, you know, fundamentally harder problem. Um, well, if humans can't do it, surely it's AI complete. So, apologies that the wrong abstract got set in initially. If anyone saw my initial abstract, you might have been confused and thought, oh, this is a workshop on negative results in natural language processing. And here's an abstract that purports to present a couple, I guess, in traditional sense, positive results about not NLP. But what I'm going to talk about here is going to be mostly, but not 100% email focused. It's going to be, so I guess, it was cool to get invited to this workshop. I took a look at, I was thinking like what work that I've done falls into this bucket. And then I guess I realized that we've actually had quite a few of what maybe could be characterized as negative results. And I'll get into, what my interpretation of a negative result is. And I think we've overloaded the term and meant a few different things by it. And I think we sort of, like a lot of sort of fuzzy words, I think we sometimes slip in a sort of sly way between different sort of meanings and negative results. And I want to be a little bit clear about what I mean. But I guess for one of these meanings, I think we actually do have a reasonably substantial body of work. And I want to talk maybe about some of those specific papers rather than focusing on one thing, to speak at a little bit of a high level about negative results more generally, and then to go through like 6 examples of papers where I think you could characterize as one form of a negative results paper, and something about maybe the value of that kind of research, but also maybe something about what the amount of opportunities there are to do that kind of research sort of says about our sort of current climate in the research world and the way that we're operating, and what's getting published and what questions are getting asked and what questions are not getting asked. So a common theme here is going to be that there's a lot of times where people have a cute story about what's going on, like what works, why it works. And it's sort of supported by a body of like selective evidence that doesn't necessarily, doesn't actually necessarily back it up. And in some areas where we've actually gone in and sort of found that maybe our story of like what models are good at is wrong. Our story of why models are working is wrong. Our story that a set of techniques actually works is wrong. And it's just that maybe, somehow some of these, I guess like the commentary was sort of weird here, is that some of these stories have gained such currency, gotten to the point where, you have like benchmarks that don't really, evidence like what they sort of appear to be or what people think they do. And yet, like, you could have thousands and thousands of papers published on them without anyone realizing it. And I think that like this sort of speaks to a certain orientation towards presenting a certain kind of positive result, such that like you could possibly get to that point. I think it's one thing if like somebody published something that's wrong and nobody corrected them, and they're in a niche area and nobody's working there. The fact that like some of these things can balloon into major concerns of a community while being somehow like wrong in a fundamental way, I think is a little bit more alarming. So I'll get into it. Since there's no introduction, I always have like a slide here handy just to say a little bit about who I am in my group, and maybe that provides some context where we come from. I run a group called the Approximately Correct Machine Intelligence Lab. It's a bit of a pun. On one hand, I mean, we do a little bit of theoretical work, and I think there's a nod towards that this is, the probably approximately correct is the form of typically anything you can say about generalization in machine learning, to the extent that you could say anything a priori or theoretically. But it's also more often a nod to the fact that we're problem formulations themselves are usually only kind of like approximations of like really crude approximations, like proxy tasks for what we actually intend to be doing. We train predictive models when our goal is to make decisions. We often don't even communicate that fact. We say an AI is going to do this, this, and this, and improve healthcare and make things personalized. But we don't actually train things to personalize stuff in a way that causes any kind of benefit of like the actions that you take when you actually do said personalization. What we do is we train things to predict what people are going to click, predict what would have happened to a patient if they were treated with something, but not actually in a coherent way deal with the counterfactual, and just kind of hope that this sort of like approximate problem formulation will just turn out by some, God will be nice to us and it'll turn out to work well. So, we zero in on problems in healthcare and natural language as maybe application domains, but we back out to these questions of like, what are we really going after? The causality. We focus a lot on ways that our technology, which seems really good, dies under various perturbations to the environment, and that our sort of claims that are built on performance and IID scenarios, but really where the claims sort of seem to transcend the IID scenarios sort of really don't hold up. We focus on interactions with other agents and the ways that there are incentive effects and kind of like economic type dynamics that emerge when models are deployed in the world. And in particular, we focus a lot on thinking about how to incorporate societal desiderata. So it's kind of a wide, so I think I'm not going to talk about all these concerns. I'm going to zero in really mostly on the like technical machine learning side and mostly on applications to NLP. So what is a negative result? I just want to say, as I'm sure other people have like, come in with their side, but I just want to differentiate a few different things. And I want to maybe just like provide like what to me is like my sort of sobriety on this topic, because I think there's a tendency sometimes to say like, just sort of like, hey, like we only publish positive results. We need to publish negative results. Everyone should publish negative results. Someone like has an experiment that doesn't work out, but they write a paper about it and then it gets rejected, and they complain on Twitter and say, see, like the whole thing's broken and the reviewers are mean and nobody's, respects my negative results. And this is why, all the incentives are wrong. And I just want to like paint a little bit of like a finer brush that it's, we don't accept all positive results either, right? There's plenty of things where you can have a hypothesis that for some reason, we think it's, obvious, or we think it's trivial, or we think the result, even if it does come out, is not interesting or doesn't have, there's a lot of papers get rejected for a lot of reasons. And the question is, what do we even mean by negative result when we draw this distinction? And why do we think, what actually is like the bar for why some negative results are worth publishing? And is it necessarily the same bar for like positive results? Like if we have a paper that could turn out positive or negative and is equal in all ways, should it necessarily be the case that if you would publish the results if they were positive, you would also, accept them for publication if they were negative? And I'm going to take what maybe in most audiences would be a non-contrarian point, but in this audience is like a, ambassador of like a negative results type research, maybe it would be a contrary position to say that no, like it probably shouldn't be the same evaluative standard. So to start with, what is a negative result? And I think there's one form of what people mean by negative result, which is either like in some form of like we failed. And when I say we failed, I mean like either one is you have hypothesis-driven research where the experiments just sort of reject the hypothesis, it just turns out not to be true. And then you say, okay, well, should we publish this? And there's a huge danger if you don't publish this, which is that you create a censorship bias, like in that, right? You only see the positive results, but you have no idea, like when you see like numbers for statistical significance, you have no ability to in any way intuit what's going on, to what extent the significance of reported results is an artifact of multiple hypothesis testing, an artifact of the fact that, like, well, a million people try out a million hypotheses, and only the ones that get significant results are published. So, okay, if I have a 1% false discovery rate, now I publish 10,000 papers, and I have a literature that paints a picture that all of them are true, when in fact, all of them are false, and they just happen to be the ones that got lucky out of a much larger pool. Okay, so there's like one argument there. But on the other hand, I don't think that's most of the research that's taking place in the machine learning community. I think that it's a mode of research that I value and that I try to engage in a lot, and that I think maybe is undervalued for the most part. Although I think NLP is one of the communities where, like, you can publish hypothesis-driven research, or research as of like a you're not proposing a new model, you're not chasing a leaderboard, but it's not the mode, but it is something that you can publish. And we have a hypothesis about some phenomena or something. I think it's sort of overall like an empirical friendly venue. It doesn't mean every paper will get published, but I think this is a thing we've navigated many times. And yes, you sometimes have to debug a reviewer, but it's okay. But now another thing that people mean by a negative result of the first category, of some sort of like we failed or our project failed in some sense, is we had an idea, like we had a hack, we had a trick, we had a heuristic, and we proposed it, and it didn't lead to it didn't lead to a gain in performance. Now I just want to zero in on those two, where like I think that these, you could sort of say that you could try to like subsume the second into the first in a very tortured way. Like you could say, oh, well, a heuristic is a hypothesis. It's a hypothesis that this heuristic will work. But the difference is that it's not a hypothesis necessarily of like fundamental, like scientific nature. It's like a lot of the heuristics we come up with, it's not that society needs to like resolve one way or another which way this thing goes. It's not like you're saying, oh, here's the treatment, the proposed treatment for this disease. And it's important that people know if the treatment doesn't work, and it's important they know that it does work and not only publish if it does. A lot of these heuristics, it's, there's an infinite number of things you could try. And for the most part, a lot of people are trying things that it's not necessarily clear that they, have any kind of, beyond the fact that like someone claims it was intuitive to them, it's not clear if there's any sort of like logical justification for it. And so in this case, you have a weird asymmetry. And I just want to point out that like, if you have a heuristic and your heuristic leads to, it's a totally ad hoc, arbitrary heuristic. There's, something like, what dropout probably looked like to people at the time or something like that. And that's actually a relatively clean one. That's a nice one. So I'm not giving that as like a bad example, something way ad hoc. Just mean there was no theory that said this thing should lead to benefits in generalization. There was no clear account for how it related anyway to capacity control or any other sense in what, anything. So like, if you tried that and you get consistent benefits across many models on many tasks, this is like, regardless of how ad hoc this was, this is of interest to the research community because people should use it. On the other hand, if you try something completely ad hoc, I say, okay, you know what I'm gonna do? I think that I have an idea for a neural network. Every first layer should have the same parameters as every fourth layer, and every second as every fifth layer, and basically like, I'm gonna tie the parameters in a like, they're congruent mod 3 or something as I go up the stack. And that's my idea. And I get a negative result. Is that the sort of thing that should be published in the same way? Like, is that a research contribution? Does that meet the same bar for novelty? And I argue that it doesn't. I think that there is a bit of an asymmetry here. The result that why we had no reason to believe it would work, but it really does work, is necessarily like, there's a novelty in a sense of like a piece of knowledge that the community needs to know. In the case of I tried something that, I might as well have selected it as random among a billion sort of just ways of, function, like I could have, just done kind of like NumPy function salad or something and come up with a different sort of parameterization, and it didn't work. Is that really knowledge? Is that really like as big a nugget of knowledge? Is that as big a, I think ultimately when we publish things, we're sort of saying we're making a normative determination about significance. And is that as significant, an equally arbitrary idea that instead of giving massive benefits across a wide number of tasks and a wide number of models, gives no benefit across any task? If we are going to say that's significant, then we have to be ready to say that basically that people can publish an infinite number of papers by just picking bad ideas. And not even, they don't need to be guided by it, and we'll publish them all. So I think ultimately, like you could put anything you want on the archive, but I think we do make a determination when we say we're going to accept it for publication at a conference that there is that not everyone could possibly read everything that anyone could possibly write, and that there is something of a filter, and that's not being a gatekeeper, in a sense of like, you're part of the guild or not part of the guild, or, in a kind of like weird way, but you are, making some kind of value judgment. I don't think that any of us, I think if we're thinking really honestly about publication, can completely get away from that. So that's like one set of results. And I want to be clear that like, I don't think every negative result should be public. Now, I think you have a bar that you need to meet. You have to think about like, what is the standard? And I think one case is there's like really good reason to believe that this idea should work, and yet it doesn't. But you have to make that argument, I think, and I think you have to make it and meet a higher burden of proof, that like either like this thing is widely believed that it should work, or this thing, like it seems like if you follow, like if you understand the prevailing theory of this stuff, it would seem that this thing should work. And so this would be the most direct way to operationalize it, and yet it doesn't work. Okay, that I think does meet it, but I think we just be real about amongst ourselves that it shouldn't just be like, oh, it's necessarily a bias, like, in a bad sense, that it's in some aspects of of what you need to demonstrate for a sort of like engineering improvement negative result to meet the same bar as a strong positive result. Now, again, there's a lot going on here. And part of this is sort of like all assuming that everyone's acting in good faith and doing their research honestly. I think part of where things get complicated is that people aren't necessarily doing their research honestly. And so if there's an incentive, just like there's an incentive to getting the right answers on tests, that does create an incentive for people to cheat. And the question is that a problem with the incentives, or is that a problem with like integrity? And I think these are not as, I think on one hand, there's like a sort of default posture, which maybe undervalues certain types of research and is not right. But I think there's also maybe a similarly naive counteraction that sometimes comes where people act like it's impossible to publish this kind of research. And I want to say that like in general, my experience is not that it's impossible. It's that there's a higher bar. Perhaps that sometimes you encounter some researchers who have like a kind of backward set of ideas or values about what constitutes novelty in research, and you have to fight that fight, but that it is far from impossible to do this research. And in fact, I would say that it's easy. And when I say easy, I don't mean as easy as publishing like, oh, I got a 20% improvement on some major benchmark that everyone cares about, like a relative reduction in error rate. But I mean that it's easy in the sense that it is historically easy compared to the publishing path that almost anyone faces in any mature discipline. I think it's easier than publishing any paper in econometrics or in statistics or something like that. Like I think we sometimes overstate the extent to which some of this research is possible. And I just do want to inject into the conversation a certain amount of sobriety about, like, I think we do need to think clearly about which negative results are worth publishing and which are not. So that's one side. Now, the other side, like that's the side that's like the least failed. Now, the papers I'm going to present are a little bit more of the opposite side, which is sort of the, and maybe this is like, you could say, I don't know, you could say I'm like, just insufficiently self-critical or whatever, but I think it's just because we've done a lot of research that fell into the second category. So one thing that we're calling a negative result is like, hey, I did this paper and it didn't work. Or I had this hypothesis and it didn't pan out. Another side is, like we're sort of saying we're identifying that there's something wrong, like, like the contribution is not a model or a new theory, but rather to invalidate claims in previous papers. Like this is, and this again gets slippery. It's hard to draw the line for where you get here, because I actually believe personally that in some sense, a lot of research sort of only progresses in some sense according to this principle, that there's always a tinge of like there's something wrong with the previous work. The question is, what kind of wrong? Is it like their claims are wrong, or is it like there's something unsatisfying and we build on it? But like always when you write a paper, you're almost always looking at the prior work and you're like, here's the ways it's good, but you're queuing up, here's what's missing, or here's what they overlooked, or here's what's incoherent about what people are currently doing. And so I think there's always some component, but I'd say maybe elevating to the point of where the primary contribution is kind of like an invalidation result, or to challenge either the methods or the premise or the coherence of approaches that are out there. And here, I think you think, how do you just, I think these are actually, maybe an easier sell, certainly, than just, I tried something and it didn't work, because, and then you think like, well, what is the standard and what is the purpose? So one, I think it's that when claims become widely believed, now they're sort of derailing, once like incorrect research or perhaps research that is in an empirical sense, like at odds with the actual evidence, is sort of forming the like prevailing beliefs of a research community, all of whom are sort of bound by the limits of their own cognition to build off each other's work. That's sort of like a dangerous position to the community. So one value here is like, it's a cleanup job. We're stepping in and saying like, wait, these things that everybody's echoing are wrong. So it's necessary sort of in a way where the value of that work, the novelty or like the size of the contribution in some sense, or value to the community, sort of grows almost not just proportional to like the sort of intellectual character of the problem, but also proportional to like how widely believed or accepted or adopted is the thing that you're invalidating. Why is it necessary, right? And in this case, when I say why is it necessary, I don't mean like why, if there is like incorrect work out there, should we do an invalidation study? But more, why is it necessary that we do so much of it? And why do we find so many opportunities to do this on work that's sort of like kind of popular and has thousands of citations? Like why does it need, like why is it so often we require invalidation studies? And here, I mean, I think it's where we get to like this difficult question of incentives. Like, yes, there is an incentive to claim a positive result, and that incentive to claim positive results in original papers, especially in like kind of leaderboard type research, leads to, and also, an incentive that maybe people are biased to other papers accepted if they appear more novel, if they appear more complicated, if they appear to have done more, which is kind of backwards. I think if you're going to do empirical work, it's way more impressive to get a big empirical gain by doing something simple. So yes, there are incentive problems, but because of those incentives problems, the people to claim a positive result when they don't in fact have one, or to kind of present a misleading about, right, to either by, constructing their evaluation in a fundamentally misleading way, or by just not doing the adequate, like kind of like statistical kind of testing to figure out whether the results could just be explained by noise, etc. But again, I think this is where we get to like the central conundrum here of like, can we just fix this by just setting equal incentives? And I think that that's not quite honest either. Like, I think the bar, like an actual positive result is valuable in certain instances when a negative result wouldn't be. And so I think the incentive is there as long as, I think this is where you get tricky. It's like there's an incentive to do better on a test, and you don't want to grade wrong answers and right answers the same way, but this does create an incentive to cheat. And you could say that the way you remove the incentive is you give everybody the same grade, but it seems like that's not also right. And so, not to say that negative results are bad grades or whatever, or everywhere, but, in that part of the taxonomy where you're saying is I propose a heuristic and it didn't work. So I hope I gave like, some sense. I want to drill down to some specific details, but some sense of like how I conceptualize this field and this set of problems. So like what I want to go into now is specifically within invalidation studies, a number of papers where basically we take some sort of like widely pursued technique and show that either something about the storytelling of why it's working or even whether it's working is like fundamentally broken. And these are to different degrees. I also want to be clear that I'm not just pointing fingers outward. We sometimes have been the victim of our own invalidation studies to some degree, like in a sense of we've done lots of work early in 2017, 2018 in the active learning space, but have also, taken a harder dig at, to what extent do these things actually hold up, or could they even potentially be applicable in the real world? Or are they resting on evaluations that are in several ways kind of misleading and shown that they are? So, we've been on both sides of this. Same with importance weighting. I've used importance weighted risk minimization in conjunction with deep learning with separable data. And then I've also, kind of taken a closer look and be like, does this really make sense? Like, we're doing it because other people are doing it. We're doing it because it made sense before we were doing deep learning when we had like model bias. You had model misspecification. You actually had to change your parameters in order to get the optimal predictor in one distribution versus another, but you don't necessarily in deep learning. So why are we doing importance weighting, and what effect, if any, does it have? And it turns out the answer is like really complicated and kind of a mess. So I'm going to drill through, again, this is not all stuff where like we're on both sides of some of this, where maybe we've been on spreading a bad story in places where we've then tried to like clean things up. But just like, just kind of like a tour of some works and how they fit into this sort of landscape. So maybe one of our first in the NLP community, I guess my first paper at an NLP conference, when I started a faculty position with originally in the business school with $0 in startup and no PhD students and no students of any kind, and since moved into a more maybe sustainable relationship where my home is in machine learning now. But at the time, I was rescued by a pack of hungry NLP master's students, and I'd done some work on recurrent models, and so we started working together. And I guess this was when I first started publishing in NLP. I guess I worked with text data, but not necessarily publishing in NLP conferences before. So our first paper at EMNLP, we were looking at reading comprehensions. We were motivated by problems in healthcare. We were interested in figuring out to what extent we could maybe answer questions based on information contained in, the biomedical literature, stuff like this. This is work with my student Divyansh Kaushik, who some of you might know. And so, I was completely new to this. So I hadn't done any work in QA or reading comprehension as it sort of, let's say, optimistically termed by some. And so we were both new to the topic. And so I asked Divyansh to sort of just kind of like loop me up. Like, what are people doing? What are the models? How does it work? How are they set up? How are they parameterized? And so Divyansh came and he started, showing me, okay, this paper does this, this paper does this, this paper does whatever. And so as we were looking at it, I started asking, we had this conversation, we started going back and forth, and at some point we had to ask, like, well, okay, they say this model's, got these sophisticated, this architecture is designed in such a way that it's, aligning the question to the passage in order to produce the answer and doing all these things that somehow there's some story about how this should result in synthesizing information from both the question and the passage to produce the answer. And then at the end of the day, what they do is they just say, okay, and here's my performance in terms of how accurately I predict the answer. So you have two inputs, a question and an answer. Ostensibly, the like taken as a article of faith is that answering the question should somehow require that you are actually know what the question is, and that you have somehow intelligently taken into account the interaction between the question and the passage to produce the answer. But the proof in most of these papers was just to say, here's our result, like here's our F1 score at this task. So the question we asked is just sort of like, and I would point out, by the way, that a lot of these tasks are created in kind of programmatic ways. So a lot of people haven't, they've come up with some heuristic for how we could take a corpus that is not a QA corpus, not actual questions or not natural questions, as some say, in passage, but just to take basically a corpus that's not a QA corpus and do something like, okay, we'll take a CNN article, we'll take a bullet point associated with the CNN article, we'll identify a noun phrase in the question, in that bullet, we'll drop it. We'll call the question with a blank in it, the bullet with a blank in it, the question, we'll call the noun phrase that was dropped from it the answer, and then we'll call the corresponding article the passage, something like this. So people have been creating these data sets, and there's a huge value to having data sets because we're sort of always marching forward thinking what's the next frontier for, to conquer with our models. But in the rush to do it, we've sort of have a lot of data sets where they're created in a programmatic way. So people haven't really verified precisely or haven't thought maybe deeply enough about what's actually in the data set. Maybe no human has made contact with most of the examples in the data set. It's unclear what's actually required of a model to answer it or just how easy or hard the task is. And so you have, a lot of things, this baby benchmark spun up that had 20 different subtasks that were part of it. There were, a million others, CBT, CNN, Squad, all created in different ways, different degrees of thought for different aspects. Some of them with humans in the loop on every stage, like the way a lot of like the sort of like span selection ones like Squad were. Others that were created programmatically, but you had this sort of like hundreds of results being published where people just basically saying, here's our model and here's the performance achieved. So one of the first questions was like basically, being like a simple person, like, it's like you give me a problem. The first thing I want to know is like, what is the best performance I could get? Like for any machine learning problem, use me out. First thing I want to know is what is the performance of the blind classifier? And by the blind classifier, I mean the best possible performance you could achieve if you covered your eyes and never looked at the input. So all you know is statistical aggregates, like the base rate, for example. If you have a binary classification problem and someone tells, you see this all the time when you see like a corporate presentation, someone says, hey, like we have an earthquake predictor and it's 99% accurate. What they don't tell you is that it's 99% accurate because 99.999 days out of the year don't have earthquakes. And so you could be 99% accurate in the manner that they're reporting without doing any AI at all, just knowing that like, what is the frequency of earthquakes? So there's always this question of like, what is actually the relevant baseline? Like, like the dumb baseline, for accuracy is not 50%, it's whatever's the base rate or whatever is the majority class, I should say, base rate, not necessarily like whatever you call the positive class. Because the positive class is 1%, then the base rate is 99%. And for every metric, you'll have a different thing. Like if you have F1, like for accuracy, if the base rate's 1%, then the blind classifier gets 99%. If the base rate's 99%, the classifier also gets 99%. That's not true for F1 score, right? For F1 score, if the base rate's 99% positive, then you can get close to 100% F1, versus if the base rate is 1%, then the blind classifier is going to get, just a little bit better than 1%. It's going to be the harmonic mean of 1 in 100, right? Of 0.01 and 1. So the question is like, we have to ask this we see this stuff all the time when people say, I think when in binary classification, it's sort of dead obvious to people to ask this kind of question if you're a data science professional of any kind. But, if you're a corporate, like kind of salesperson, they might elide it. But a data scientist just knows to ask this question in binary classification. We think of it as like an elementary error. So we look at what's going on in these papers. We find a lot of these papers, basically we ask like, what is the performance? Like, what is the blind classifier doing? Like the relevant notions of the blind classifier here. And so I'll tell you what I think they are, or we thought they are. We thought that Divyansh and I thought about this. We thought like, well, immediately sort of what happens if the classifier only looks at the question? What happens if the model only looks at the passage? So like how good could I, like if I'm going to make an argument that I'm getting great performance, I'm getting great performance because I'm attending to both the question and passage in some kind of sophisticated way, I should know how my performance stands relative to if I apply the same model and it couldn't even look at the question. I need to know because that's like the relative gain by virtue of the fact that I've modeled this interaction. So we asked basically, what is the question only performance of these models? Like very simple questions like this. What's like, what's the question only performance? What's the passage only performance? How do we know? There were some tasks where they prided themselves on the fact that the passages were exceedingly long. So you have to deal with like long form context. So we just asked, okay, if that's the point of this benchmark, and that's why that's what's the sales pitch, and that's also why all these other models downstream are these other papers are using it. Let's just make sure, does it actually require that you look at the whole passage? Or could you, for example, have just looked at the last line of the passage or the last 4 lines of the passage? And basically what we found is on many data sets, like for example, a large fraction of the baby task, but also, a whole bunch of the others, QA benchmarks, like to different degrees, models trained on either question only or passage only data matched the numbers, like sort of did just about as well as the numbers of the models that people were reporting literature for models that ostensibly were actually doing something sophisticated to account for the interaction. So basically their evidence was we're doing well on the leaderboard, but we basically showed that like, okay, the simplest pushback on that, the simplest attempt to poke a hole in this, poke the hole in it. So on one hand, this is a good thing in that like we sort of corrected the literature a little bit, and Divyansh got a best short paper at his very first submission, and it was great. On the other hand, we shouldn't have been able to write this paper, and so I think it's worth thinking. There's like I think both sides here. Here's an example of a negative result. It's the kind of negative result that's easier to sell because it's a negative result on something that is. It's like, it's not that we did something wrong, but we want to publish it anyway. It's we did the cleanup job, but the form and the result is that there's something kind of wrong in the literature. But at the same time, like, I think it's okay for there to be isolated mistakes, but I think it does point to a more systematic problem that we got to the point where we had thousands of papers all tackling these problems without anybody reporting what is just the sanity check, like what is just the relevant notion of the base rate, and it's important because it's not just that you always match that number, but it's that in a lot of these tasks, even where the passage only or question only baseline doesn't match the number that's reported, a lot of them it still does surprisingly well. So it's a surprisingly strong baseline, and it's necessary for the same reason that, when you report the 88% accuracy and you get excited about it, it's really important that you know that this is relevant relative to an 82% for the blind classifier, not to 50%. Right. And again, we found also for some of the ones that tasks are ostensibly challenging because of the long passages, you only needed to look at like one sentence or the last 3 sentences, or maybe if you look at the last, whatever it was, 5 sentences or something, you got like 90% of the performance. So I forget the exact numbers, but the high level detail here was, it's like this is an example of a negative result. It says a little bit about, maybe the fact that like maybe the research would have moved faster if the publishing moved just a little bit slower, and we're just a little bit more thorough. And where a negative result, of at least the invalidation kind, I think did provide some value. A point, oops, sorry, the out of order slide. Another kind of instance of this is in the case of adversarial data collection. So basically, people have all these QA data sets, and you train models on them, and they perform well. But because among things like what we showed in our paper, that a lot of these benchmarks are sort of flawed in some way, or there's somehow or another the model is not really doing question it. It's like this kind of difference between what we actually train the model for inside the machine learning sandbox is like the ML task, but then there's this like real world, more general task that we care about. And we think that like, okay, the models learn like the task, but not the task. It's learn the ML task, but not like the real task for which it's a surrogate, where here the real task, presumably is doing question answering in a variety of environments, and that even somehow that like the form of what's going on is the model actually is taking the question into account, so it seems like, but again, I think this is where we get confused, that we, the ML tasks are expressed in statistical language. And I think that what our intuitions are not about statistics, are about reasoning, and they're about these things that the models just fundamentally aren't doing. So we kind of this weird mismatch. We go back and forth, and we say, well, we need to know what the model's reasoning is. But the problem is, if we wanted reasoning, like, well, we were never in the reasoning business in the first place. We were in the training statistical models, flexible statistical models by updating their parameters by stochastic gradient descent world. So what a lot of people have done is say, well, okay, you can expose these flaws by like designing, change the question such that it changes the answer. It would fool the model. And so, one idea is, some people might say, okay, we can make a harder benchmark by having a model in the loop, and by people basically take the previous model as trained on the original data and now come up with questions that fool the model. But I point out that, like, even if people just sort of say that in papers, that's not really the full normative story. That's not why we care about it. It's not if you want a hard benchmark. I'll give you a hard benchmark, I'll assign the labels randomly. Now it's hard to get good performance, but that's not interesting. Or I can give you a hard benchmark where the labels are not assigned randomly. They're assigned deterministically, but they're assigned according to some like cryptographic function. That's a hard benchmark, but it's not interesting. It's not what you care about. So we don't just want to make them hard. We want a model that is like actually doing question answering, in the sense that like it's not just picking up that like, okay, in this particular data set, there's some kind of tell in the passage that by itself tells you what the answer is going to be, so you don't actually have to read the question. And so you get out a model that ignores the question. And then if you do change the question, which you keep in mind is like going out of distribution, you're now evaluating in a world where the questions are changed. These models are breaking. We don't want them to break. So, ostensibly, we'd hope that by creating these data sets in this adversarial fashion, where we're trying to probe for the model's weaknesses, that when we then train a model that's trained on both the original data plus the adversarial questions collected with a model in the loop, perhaps plus yet more data collected with a model, with like the second generation model that is now robust, trained on the first collection of adversarial examples. Now that one in the loop, okay, if you do this whole process, you should come up with a model in the end that generalizes better to data that you haven't seen before, like not just to like weird people trying to game things, but that you've actually closed these weaknesses such that the model would perform better out of domain in like other related but not identical data sets that were collected by different people on slightly different data. So what we did in this paper, and this is also work by my student Divyansh Kaushik that was done with a bunch of collaborators at Facebook AI Research during an internship, and give credit also to Dawe and to Scott Ye, who are Divyansh's mentors over at Facebook, and were really fun to work with. Scott, my old friend, one of my interning sort of mentors, unofficial mentor back when I was at MSR as when I was an intern myself. So we had this paper together where Divyansh was basically working real closely with Dawe Scott to like create an interface for doing this adversarial data collection at scale. And one question, relevant question we ask is sort of like, well, when you've collected data in this adversarial fashion, how well do you generalize to these now because we were already generalizing well IID in the first place. So the question is, when you collect this adversarial data, how well do you generalize? And not only to the held out data that was also collected in an adversarial fashion, but also just out of domain to a bunch of other sort of related QA tasks that have like, the same basic construction and, somewhat overlapping like topic matter. It's not like you're generalizing from like English to Klingon, you're generalizing from, squad to natural questions to whatever, et cetera, et cetera. So they conducted a lot. And the other thing is that there's papers published on adversarial QA. There's papers published that collect data in a non-adversarial fashion. However, each paper is a different paper. So they're different in all kinds of ways. They're not scientific studies that are actually comparing the different mechanisms, because you have a different cohort getting paid a different amount of money, selected according to a different selection criteria. So the idea is to do actually a randomized controlled trial. And in a sense that you're going to recruit a whole cohort, and you're going to basically assign people. So it's the same underlying pool of workers to either be creating work data in an adversarial fashion or a non-adversarial fashion. And then you're going to train models on the resulting data and see how they generalize. And the high level, sort of important takeaway here is that data generated in an adversarial fashion led to QA models that generalize way better on other adversarially collected data. However, these models perform strangely badly on non-adversarially collected data. So, we think we're like, by patching up the vulnerabilities, getting models that are sort of more generally good at the task of QA. But what we got instead was models that fail when you go, they do much worse when you go to other domains than the original IID model. They only do better when you evaluate it on other data created by crowd workers trying to fool models in an adversarial QA fashion. So here's a case where we're not saying that the result in the papers is wrong. It's not that the quantitative result, again, but it's that it's saying that like, hey, like there's a motivation mismatch. The story is wrong. Like, the center, like a big pillar of the story has been that this is going to lead to models that are more generally, doing better at QA. And we've somewhat sort of patched up the vulnerabilities such that this model can perform well, even if we were to go out of domain a bit. But it seems that they only perform well in a precise setting of crowd workers trying to game the models, but not actually in, and this was like felt fairly consistent across, we had, I think, like, over 10 like challenge sets that we were going to. 2017, we had a paper that was published at ISCLR 2018, where we were trying to see, at the time, deep learning was still like kind of new, in that there was a lot of the, adapting ideas into deep learning was a pretty natural genre, and like a lot of work that a lot of us, kept us busy for a few years of like, okay, we have some tools for active learning, some mixed evidence of are they effective or not. Well, are they effective in the context of deep learning? Active learning seems especially well motivated in the context of deep learning because these models are so data hungry, right? So it's like, okay, if deep learning requires a million examples to get to some, close to its potential for some task, say named entity recognition, could we have used 10% of the data or 20% of the amount of data if only we had collected it in a strategic manner? Collected it in this case means the typical active learning setup where the data is initially unlabeled, you have some big pool, and you're going to basically pick which example to send out for querying the label and to get the label back. By the way, Zhao, I have just like let me know like when I've got a 5-minute warning. I know that I'm like about probably where I was supposed to end originally. I know we started a little bit late, but I don't want to push everyone else back. So just maybe give me a 5-minute warning, and I'll wherever we are. But so basically here we had this kind of story, which was like, okay, let's try all these different heuristics for doing active learning and see if they work. And it's super expensive research from a computational standpoint, because you got a deep learning model in the loop. So it's like, okay, I've collected 2% of my data. Now I select some batch of examples for which one should get labeled next. I send them out, this is like all simulated. So I actually know the labels, but I'm just hiding them from the model. I like allow the model to query those labels. It gets the labels. Now it's got to retrain the model or either fine tune it on the augmented data set where you've added the new labeled examples, or you have to just like retrain from scratch. So it's like, okay, I'm training the same model like 100 times to get from beginning to end, even to like get just like a handful of training runs across different techniques, including both some methods that we're trying to do something clever with like submodularity, so you collect a batch of examples that are, within the batch diverse somehow, versus, doing some kind of traditional like least confidence heuristic, versus trying to, use uncertainty estimates that come out of some Bayesian approach, so what we call BALD, like either using like the dropout approach for getting these like, sort of like parameter uncertainty type uncertainty estimates, or we also use like networks like Bayes by backprop type now. So we tried doing all this stuff. And indeed, we found that like at the end of the day, we had a model that got to basically 99% of the performance of the full deep learning model using 25% of the number of examples. This is a positive result, right? It's a claimed positive result. But we kept thinking about this, and so then the next step was, again, that first year, 2018, when I was working with a talented student named Aditya Siddhant, who's now at, I believe, still at Google. But really incredible engineer and great experimenters who think like, what can we do with like, if I were able to run way more experiments than I personally am able to because I'm a lousy coder, what could we do? And so we started thinking about this active learning problem again. We thought, well, hey, it sounds great on paper. Like, I pick examples in a strategic way, and I get to a good model in a more data efficient manner. But active learning in general is like a funky area. There's, toy thresholding problems where you can actually show like a rate improvement, that you have like an exponential decrease in the number of examples required to reach a certain accuracy level. And that's amazing. That's great. That like inspires this whole area to think like, wait, maybe, okay, it's like, I want to identify the threshold. If I do binary search, I get exponentially close, like in the number of queries, versus if I'm querying randomly, I get better at a much, much, much slower rate. That's intriguing. But on the other hand, in general, even in linear settings, like agnostic, like linear settings, meaning like not separable linear settings, with like data distributed uniformly on like the hypersphere or whatever, in general, there's already some negative results theoretically. It says active learning is not, in the worst case, no better than just IID querying. So it doesn't mean that there aren't other sets of assumptions where it could do better, but it means that it's not like active learning, any of this stuff is guaranteed to be better. And in the worst case, it's at least as bad as IID. So, okay, we've got this one thing that seems to be working. Do we actually believe our evaluation? And, it's one of these things where it's like, everyone's so used to being like, I did this, I did this, I did this, I did this, I evaluated on the test set. But, we have to think about, is that, like as people start setting their eyes beyond just doing vanilla, like supervised learning, you have to think like, is that really the right evaluation? So here's like one issue. One is that hindsight is 20/20, but not foresight. So what are we doing here? Well, we're iterating on our experiments. We're trying lots of approaches. But we're then like, a lot of them could do worse or no better than IID sampling. But then when we find a good approach, we say, okay, this one is, okay, this guy's great. We have an improvement over IID. So the problem though, is that this is like, this belies like the actual fundamental motivation of active learning. Because if I had to train the IID model to know how good it does, and then I had to train a bunch of different active learners, each one of which got 20% of the data, until I found one that using its 20% of the data did, like almost as well as the IID model, then it's like, well, I didn't really use this number of examples. I actually had to use the amount of examples to try all the approaches. So the question is, if I freeze this approach and I go to a new data set or a new model architecture, any of this stuff, will it also be that this guy does really well, that active learning does really well? Or will it be that like, in order to get what appear to be the benefits of active learning, I'd have to actually run 10 active learners, which would actually mean querying all the data, in which case I might as well have just queried all the data in the first place, in order to then be able to say, okay, on this data set, that guy was the winner. Let's use that one and use its 20% of the data. But really, we're using 100% of the data, because if it's not consistent, which method gets a gain? So the question was like, we can't run 4 strategies or 40 strategies or any of this and retrospectively pronounce a winner. We can't use the full set of labels, pick an architecture. So we actually were after a negative result. That was our goal, was to say, okay, supervised learner, can mess up, because you can do whatever you want on data, keep training on data, keep looking at the validation data, go back and forth, back and forth, back and forth, until you get a model that does well. And it turns out that adaptive fitting is actually quite slow if you're just actually acting in good faith and only using your validation data to, make like, hyperparameter choices, like architecture type decisions, not actually like hard coding answers, for reasons that are not fully, understood, but is interesting kind of outcomes of like these replication studies, that adaptive overfitting is not quite the pox, that it could be, theoretically. And so the question is to say, we're after a negative result, to say, if we took, we trained, we took many tasks. For every task, rather than looking at one task and 1 to 2 data sets in one model, we took many tasks. For each task, we took many models. For each task, we took many data sets. For each task and data set, we took many models. For each task, data set, and model, we tried each of the several active learning techniques. The question is, would we find any active learning technique that consistently does way better than IID sampling across, across task data sets and model architectures? And we were, basically, we were expecting to find like, actually, this whole line of research has a deep, deep, deep problem. And here's a weird thing is that like, we actually had a positive result, a surprising positive result that jumped out to us. Like we were not expecting, it felt wrong to us. We found that this model performed, that basically the sort of like Bayesian active learning by disagreement, whether you get your disagreement from dropout or from weight uncertainty by using the Bayes by backprop approach, they both seem to work well across data sets, models, and architectures. Task data sets, models, task data sets and architectures. So this was like a surprising positive result where we were actually oriented towards like cleaning things up and close. So it was like, okay, in this case, I point out here, there's multiple things. One is the stories can get more complicated. So it's not so clean, cut and dry. But one thing here is that like, chasing a negative result is often if it invalidates a positive result, then it wasn't a real positive result in the first place. You've done a service to the community. But if you like really stress test the crap out of an idea and it survives, that's also a value to the community. And so there's an orientation, there's like a value, not just of a negative result versus a positive result, but I think of like the mode of inquiry that is concerned with, rigorous experimentation, or is concerned with like really putting things to astringent tests, seeking clarity rather than seeking novelty of the variety of methodological novelty rather than like scientific novelty. So there's value even when an attempted negative result turns out to be a positive result. It's like, you put something to the test and it passed. However, things are a little bit more complicated. So we revisited this work with a different mode in mind. So, I said before, there's multiple ways you could attack work. One is you attack, are the results even really believable? Or is there something fundamentally flawed in the method or the evaluation or whatever? Another way you could attack other work, though, is thinking like, is there like a fundamental contradiction of like, is the method actually sort of ill-motivated? And when you put it in the context of the correct motivation, does it fall apart? So in this case, we had a different insight. And this is a work with Byron Wallace and David Lowell, who was his PhD student at the time. That was published in, I say EMLP. I'm like a little dizzy. It's like, not EMLP 2021, EMLP in 2019, I think. So the premise is we looked at it and said, active learning, that there's this weird thing. Active learning, you've coupled the model that you're using to collect the data. You're usually using a model in the loop, and based on its predictions and its uncertainty estimates, et cetera, deciding which data to collect next. However, if we look at real world applications of machine learning, there's a common pattern, which is that data sets usually have a longer shelf life than models. So, it's not always true. For example, if you're like a recommender system on like a site where like the inventory is changing quickly, they might be retraining their models nightly, and the data sets might be refreshed way more at a way faster clip than the models are. However, most academic problems, even a lot of industry setups, the models are changing very often. The data sets are changing infrequently. So in that case, we're using one model and using its uncertainty estimates to decide what data to collect next. And then ultimately, that's the same model architecture that you're using for the final model. What happens if actually you use one model to collect the data and then, use the LSTM to collect the data, and then, 1 year later, now we have to convert everything to transformers. Even when you do observe a benefit in active learning, how often does it survive the leap to, a new model? Like, does the motivation fall apart if you're in this world where you're actually planning on keeping the data set for a while? We ended up finding, in this case, sort of dubious outcomes. So here, models sometimes outperform, but more often they underperform random sampling when you use there's a different acquisition model and like successor model, like subsequent deployment model. So this is like kind of cuts the foundations of like, is this active learning actually useful if we really care about the data that we're collecting? But here's another thing we had. We had difficulty replicating the broad success of active learning in the previous paper. And this is really scary to us because we create, or not we, but like me, like I was a co-author of the previous paper. So it's like, what's going on? And not only that, the previous paper wasn't looking for a positive result. The previous paper was hunting for a negative result, and yet we found a positive result. So like, what's going on? Okay, cool. I got a 5-minute warning a couple of minutes ago, so I'll have 2 more minutes. So it turned out that like, basically what happened was the student on this project wanted to recreate the entire code base from scratch, wanted to like get that experience. He was a first-year PhD student at the time. And in so doing, made one tiny modeling decision. So even though we thought we were being so thorough, we looked at different tasks, different data sets, different architectures. The one difference, he looked at the same tasks, same data sets, same model architectures. However, the only difference was for like these BiLSTM models were the base representations given by Word2Vec or by Glove. And it turned out that this is what made the difference. So we're saying active learning works versus doesn't work. And it turned out that like whether or not active learning seems to work depends on this one, some random factors that like you have no reason to believe in the first place that they should be the things that make a difference. Why should which pre-trained word embedding I use make a difference? It's like, seems like an orthogonal aspect. So now I'm going to really blitz through and just give a high level of some other ones and just give like the 1-line summary of where I've had some really good results. One is attention. There's like a kind of whole folk literature where people just act like on faith, like looking at attention maps tells you something about the model that produced it, tells you something about how it behaves. So we basically figured out, can we get models that behave identically on almost all data, but give you radically different attention maps? And not only that, but in ways where like they provably depend in some really important way on the inputs that they're not really paying attention to. Like a model that gives predictions for like who should get hired entirely based on the gender of the reported gender as reflected in the gender pronouns and other gendered words. Like I don't know, waiter versus waitress, right? Like in the document, but that appears to pay no attention to them based on the attention map. So we've created a slight perturbation to the objective that basically just told the model it should cast attention in a different way. And it turns out we can learn models that sort of provably depend upon, in a very important way upon these features that, appear not to matter if you look at the attention maps. Basically, train identically to their models if you didn't, perturb the training objective in any way on just about every single example in the holdout data. However, the models appear to give you a completely different attention map. And so there's this whole literature, like just acting like on faith, like these things constitute an explanation of the model's behavior. That just show there's an infinite number of different models, all of which have the same behavior and all of which have different attention maps, which means you can't draw a direct line from, the attention to some deeper property of the model. Any sort of connection that does lie there flows out of like a sort of unknown process that we have no right to have any expectations about, that sort of like depends upon the unstated implicit biases of stochastic gradient descent on the original objective or something. So how's this work? What else have we done? People do importance weighting in deep learning. Why? Because it's like, okay, well, at deployment time, these classes are going to be weighted differently. So let's reweight the distributions so that they're basically, if you had done this on the underlying measure, you would actually make the distributions identical. But in this case, you're just reweighting a finite sample. Importance weighting makes a lot of sense if you have model misspecification. That's well known since forever and maybe introduced to the applied stats community in like 1999, 1997, and 2000, something like this, by like Shimodaira and subsequent papers like Shimodaira, Sugiyama, these guys. So covariate shift correction by importance weighting makes sense if you have model misspecification. But deep learning doesn't have model misspecification. In fact, it's almost, at least in like a lot of these NLP tasks, and certainly in most vision tasks, where a lot of the ones where we're applying importance weighting in various algorithms throughout the literature, models are just shattering the data. They're perfectly capable of separating data. And a lot of them, they're capable of separating the test data. They just don't necessarily separate it because you don't have enough examples, but they're not actually model misspecification. So in this case, what is the impact of importance weighting? And it turns out that like importance weighting appears to have an impact early in training, but actually as you train for multiple epochs, the detectable effect of the importance weights, even for extreme weights, like over 100, like 256 to 1,